Okay, I think we're ready to go. Hi, welcome to today's Chaos Talk. Today we have our own Dr Natasha Maddox in to give a talk about her work in radio astronomy. She's recently joined the university after working in South Africa as part of the SKA. She did her PhD in Cambridge on the infrared properties of quasars. We have donuts ready to go in fizz bar for when the talk is done, and the next talk after this is in 2 weeks' time here, same time, and it's being done by the namesake of Berry Electric Theatre, Sir Michael Berry, on the history of optics. So yeah, that's going to be a talk. It's going to be a talk. So yeah. And with that, I will pass off to Natasha. Thank you very much.
Right. So thank you very much for having me. I've heard only good things about your society. I hope I don't disappoint. Everyone's here at 6 o'clock. It's a little bit late, so. Hopefully it goes well. I'm sure it will. So when I was putting together the introduction, I thought, okay, well, so I'll tell you a little bit about what I do. And then I thought, well, I do something quite niche in astronomy, so I'll have to sort of take a step back and talk about the type of radio astronomy I do. And then I thought, well, maybe not everyone in the audience has even taken an astronomy class, so I'll take even further a step back. So we'll start pretty much right from the beginning. So we'll talk about radio astronomy, various telescopes, MeerKAT, which is a new telescope, SKA is a telescope in the future. Talk about H1, neutral hydrogen, what does it look like, why would you study it, and then a few results from recent work that I've been involved in, and it turns out that if you explore new parameter space, you make new discoveries. And then hopefully by the end of this, you'll be convinced that radio astronomy, and specifically the SKA, are one of the new growth areas in astronomy and physics. So this is the center of our galaxy, the Milky Way, taken with an optical telescope, and basically all you see is stars. There's just stars everywhere. There's down here in the bottom corner, if you can see my cursor, that's the Large Magellanic Cloud and the Small Magellanic Cloud. These are our neighboring galaxies. They're sort of gravitationally attached to the Milky Way. And then all of this black stuff is what's called dust. It's basically interstellar soot. It's little grains of carbon and silicon, and it blocks the light from the stars behind it. So this is what the center of the Milky Way looks like at optical wavelengths. If you look at the same patch of sky with a radio telescope, so this is now radio continuum, which measures electrons whizzing around magnetic fields, so it's synchrotron radiation. It looks very different. So the color coding here is, it's basically based on energy. The center of the galaxy is not blue. It's just a color coding that you need, but it looks very different. I think we all agree there's these sort of filaments, various things. There's all of these bubbles. These are all supernova remnants, all kinds of things going on in the center of the galaxy. So what that means is that what you see depends on how you look, what telescope you use. So optical telescopes, I use this one as an example. Every telescope has a name. This is called the Very Large Telescope because it is very large, the VLT. It's in Chile. The mirror is 8.2 meters across. So this is a picture of the mirror. There's little people here. For scale, there's a person. So this is a big mirror. It's actually one of the largest. It's the largest single piece mirror in the world. And its surface is accurate to about 20 nanometers. So this is a smooth mirror. The reason it's so smooth is because it needs to be some fraction, like a 10th or a 20th, of the wavelength of the light that you're receiving in order for it to not distort your image. So the wavelength of visible light is about 400 nanometers. A 20th of that is 20 nanometers. So it has to be this smooth to get a clear picture. Radio telescopes, so if we know that the surface accuracy of your mirror or your dish has to be some fraction of the wavelength of the light that it's measuring, radio wavelengths are long. They're about a centimeter, 20 centimeters, or a meter. A 20th of that is actually substantial. So radio telescopes can be a bit rough. Sometimes they're actually just made of mesh. What that means is that it's easier to make bigger dishes, bigger telescopes. So here's one example. This is the Lovell telescope in Jovra Bank. It is 76 meters across. You can see the trees there for scale. It's a big dish. The white part is the dish. It focuses the energy to that middle stem there. That's where the receiver is. That's how it works. Even bigger than that is the Green Bank telescope, the GBT. It's 100 meters across. So for scale, if you think of athletics tracks, that's how big this telescope is. And then I found this little quote on their website. The Green Bank telescope is 485 feet high. It's 17 million pounds and has a dish 2.3 acres. And then it says the GBT is the largest moving structure on land. There are larger structures that can move, but they're all in water. So these are cruise ships, aircraft carriers. But the largest moving thing on land is a radio telescope in West Virginia. Even bigger than that, there's Arecibo. It's 300 meters across. This one doesn't move. It points straight up. And it's a good example of how rough your dish can be in radio astronomy. There's like moss growing in the middle of it and stuff. So it just points straight up, and it waits for the sky to go past. It observes whatever's going past. You can point it a little bit. This is the secondary here. You can move the secondary a little bit, so you can track pieces of sky, but you can't move the dish. You can't point it around. And that secondary is supported by these big poles, these big towers. Maybe you saw in the news that it collapsed. So this is the secondary. This is one of the towers. So Arecibo is no more, which is very sad. There's an even bigger one, 500 meters across, called FAST. It's in China. It's the same design as Arecibo, it just points straight up. Instead of just building bigger and bigger single dishes, let's be a little bit clever about it, because that's difficult and it's also expensive. It's a better idea to build lots of little dishes, which are cheap, and then you connect them electronically. So I've put little asterisks here because I could give you, or someone could give you a lecture for hours and hours about what it means to connect the signal electronically. It's not that trivial, but fundamentally for this discussion, that is what you do. You have little dishes, you connect the signal electronically, they behave as though they are one big dish. And that's a sort of a more efficient way of doing things. So this picture is the Very Large Array in Socorro in New Mexico. It is 27 dishes all connected together. Each one's only 25 meters across. So this is actually quite small, right? If the Lovell telescope is 76 meters, this is only a third of that. But there's 27 of them. And for a very long time, this was the industry standard. This was the best telescope in the world for the stuff that it does. And the things that it does that are unique, it is still the best in the world. So this is it. It was also in the movie Contact, if anyone recognizes it. So a couple of details about interferometers, because it's a little bit not intuitive. Your field of view, the patch of sky that you can see in one shot, is determined by the size of the individual dishes, not by the size of the array. And if you have a smaller dish, you have a larger field of view. And it's also frequency dependent, so that's sort of a radio engineering feature. Then the distance between pairs of dishes, which are called baselines in radio astronomy terminology, that determines the resolution, how fine of details you can determine. So far apart, good resolution, but it's also expensive, right? If you have dishes that are 20 kilometers apart, you don't only have to dig a 20-kilometer ditch, you have to put 20 kilometers of cabling in there. It's also expensive computationally. So this is, so the ideal is that you build lots of small, cheap, large field of view dishes, and then you spread them over a large area. That's sort of the ideal goal of radio astronomy. And that's what the SKA is aiming to do. This is the next major advance in radio astronomy. So SKA, the name, stands for Square Kilometer Array, and it's sort of an old hangover. It was basically a couple of people sitting around, and they thought to themselves, how big of a dish would I need to make a very specific kind of observation of a certain kind of galaxy at a certain distance? And it turned out to be a square kilometer. So this is a big telescope. And the name stuck somehow, so it is still called the Square Kilometer Array. It has nothing to do with how actually big the thing is going to be. So this is an artist's impression of what the SKA is going to be. It's little dishes, 15 meters, everywhere. So you get good resolution. It's quite a big project. It's an intergovernmental organization. It has partner countries. They need a headquarter. The headquarters is in Jodrell Bank. This is a picture, so this is actually the only part of the SKA that's been built, is the headquarters. It turns out the northern hemisphere is not fantastic for astronomy because we don't have a great view of the center of the Milky Way, basically, or the Magellanic Cloud. So a lot of the new telescopes are being built in the southern hemisphere. So the headquarters is the only part that's in the northern hemisphere. They're actually building 2 telescopes, the SKA. They're building a low-frequency array in Western Australia. Low frequencies means like 100 megahertz, which has a wavelength of 3 meters. 300 megahertz has a wavelength of 1 meter. So these are, that is the wavelength of the radiation they're trying to detect. And it turns out if you want to try to detect that, you just need antennas. You don't really need dishes. So that's what these things are. They're just patches of antennas on the ground. You connect them together electronically, and they sort of behave like a big dish. And you have a bunch of those, and then that makes up your array. I don't use low frequencies so much, so I'm not going to talk too much about this anymore. I use more mid-frequency. And this is where the mid-frequency dishes are going to be. This is Africa. Every white dot is a planned location where they're going to put telescopes for the SKA mid-frequency array. So if you remember that the distance between dishes gives you resolution, this is like continental sort of distances, so the SKA is going to have good resolution. And there's this cluster of points down here in South Africa, and that's where MeerKAT comes in. So this is MeerKAT. It's South African owned and operated. It's a precursor to the SKA. And this is where it's going to, or where it is. It's in a region called the Karoo, which is now a protected radio astronomy reserve. And that's its proximity to cities you've probably heard of. So the name MeerKAT, it used to just be called KAT, the Karoo Array Telescope. And then they decided to upgrade it, make it more. The Afrikaans word for more is meer, so it became MeerKAT. So it is a good name. This is a photo. It's not an artist's impression. MeerKAT exists. It is 64 dishes, and each dish is actually quite small, 13.5 meters. With this beautiful design, the offset Gregorian design. If you remember, the VLA in New Mexico has 27 dishes, so MeerKAT has more dishes. The VLA dishes are bigger, 25 meters. MeerKAT are smaller dishes, which means MeerKAT has a bigger field of view. So the field of view of MeerKAT is about a square degree, and just for reference, the full moon it takes up about 0.2 of a square degree, so it's about 5 times the size of a full moon. And you want a big field of view because it means if you want to map the sky, it's faster. You can see a bigger patch of sky at a time. So the VLA's field of view is about a quarter of that, and the VLT, if you remember at the beginning with that big shiny mirror, is only about 1/10 of a square degree. So MeerKAT's got a big field of view. The maximum distance between dishes is 8 kilometers, which is pretty good, so it gets good resolution. And for what it does, it is now the best telescope in the world. It has surpassed the VLA. One of the things that MeerKAT was specifically built for was to look at hydrogen. So everyone normally would call it hydrogen. Astronomers either call it neutral hydrogen or H1. Hydrogen is the most abundant element in the universe. It's also the simplest element in the universe. It's also a primordial element in the universe. It's just a proton and an electron. And it is the fundamental building block, not only for stars, the forming stars, but for everything, right? Everything in here used to be hydrogen. It doesn't emit a lot of radiation. It only emits in radio wavelengths. So you need radio telescopes to observe this fundamental material. So this is a simulation, and I'm going to turn the lights down. Okay, so we'll leave it at that. So this is a simulation called the Eagle simulation. In the lower sort of wedge, that's dark matter. That's basically just gravity, where galaxies are going to form. It shows how gravity clusters and clumps. In the top wedge, it's showing where the gas in their simulations is. And gas is gas. It responds to gravity. So the gas is also going to follow gravity, so it's going to follow dark matter, but it follows it in a slightly different way. So we'll set the video running. Every time step is time. So it starts back in the universe when the universe is very young. That's why things are quite smooth. There's not really any structures. The universe was just young. And then it steps forward in time towards the present day. So if we watch this, the dark matter is very clumpy, very quickly. And it forms these big structures, and that at the intersection of those big structures, you'll get a cluster of galaxies. And the gas looks a little different. It's sort of the same, but it's fluffier. It's not quite so clumpy. And then it keeps collapsing, and then you can definitely see in the dark matter and in the gas that there's connections between these clumps. These are called filaments, and they become quite obvious in the gas. So this is now effectively the present day. The dark matter is very, very clumpy. This is a problem with dark matter. We don't actually observe things to be that clumpy, but the gas does look about right. It's fluffier, it follows gravity, but it's not quite so densely packed. So I think this is beautiful work by the Eagle simulation. So that's where hydrogen is. It's in the galaxies, and then in these filaments in between galaxies. How does it emit? Hydrogen is just a proton and an electron. They can either have their spins aligned or anti-aligned. This is a slightly higher energy configuration than this. If you leave a population of hydrogen atoms in space, some of them will have their spins aligned. They don't like that. They don't feel too strongly about it, but they don't like it. If you leave them for 10 million years, the electron will randomly flip its spin. It goes down to a slightly lower energy level. It has to emit a photon. That photon is very low energy, and that is the 21 centimeter line. It has a wavelength of 21 centimeters. So that is the photon that comes out of this electron spin flip. So it is a highly forbidden transition. You can't observe it in a lab. It only happens in the universe. So it is a spectral line. And just to remind you what that means, there's continuum radiation sources, so like the sun, black body radiation. If you take a spectrum of a black body radiator, you get a continuum spectrum. There's emission at all wavelengths, or many wavelengths. If instead you take a spectrum of a cloud of gas, and I know this because I've been watching the second year labs, that you have one of these labs, you take a spectrum of a gas and you get discrete spectral lines that correspond to atomic transitions from the gas. So you only get radiation at specific wavelengths. That's what we're observing with hydrogen. We're observing clouds of gas. They emit at one wavelength, and that is in the radio. If you pass your continuum source through a cloud of gas, you get an absorption spectrum. And you can do that with H1 as well, but that's not what I'm talking about here. So we're talking about a spectral line. The good thing about spectral lines is you know what wavelength it should be, very precisely. And if you observe it to not be at that wavelength, then you know that the gas is moving. It's a Doppler shift. So if the wavelength is shorter, so that's higher frequencies, you know that the gas is moving towards you. And if the wavelength that you measure is longer than you were expecting, you know the gas is moving away. So with a spectral line, you can actually tell movement in the gas as well. So that gives you that extra sort of three-dimensional perspective. So this is another video. It is not a simulation. This is data. This is the neutral hydrogen, or the H1, in the Milky Way. And every step, every frame in the video is a velocity, not a time. So every frame shows you only the H1 that is at that velocity with respect to us. So let's see how that looks. So it sort of starts out in the middle and in the lower left there. And then it starts building up. and building up. And then you start seeing the galactic disk. H1's always in a disk. And that's the plane of the Milky Way. So this is all stuff moving towards us, and then it switches to stuff that's moving away. And then it runs out. And then if you keep an eye on the bottom right, you see the small Magellanic Cloud pop up. So that's moving away from us. And then the Large Magellanic Cloud, which is moving away from us slightly faster. So that's what the H1 is doing in our galaxy. And we can see that movement. We get an idea of velocities. So if you then collapse that video, all the frames into one frame, this is what you would get. There's the galactic plane, and then down in the bottom right, there's the Large and Small Magellanic Clouds. What does it look like in other galaxies? Here's another galaxy, NGC 2403. It is well studied in H1. So this is a galaxy. It's rotating. You can see that it's spinning. So you can guess that the bottom part is spinning away from us. So that's receding. And then the top is coming towards us. So the H1 that's in that receding part of the galaxy, that should be redshifted, so it should be at longer wavelengths. And then the stuff at the top should be approaching, that should be at shorter wavelengths. So now this is data. This isn't like a movie for, public relations. This is just data. This is H1 data. It's a video. Every frame, again, steps through velocity. So every frame only shows you H1 at a given velocity. So that's the receding side, and that's the approaching side. And then it loops around, the receding side, the approaching side. And the center doesn't really move much. So that's what a rotating galaxy looks like in H1. Again, if you collapse all of those into a single image, you get this. So it looks like a galaxy. H1 is very fragile. It's just gas. So it's easy to disrupt. This galaxy is very regular. It doesn't look disrupted. It doesn't look like it's been disturbed. So this galaxy has just been left alone, no problems. Nothing has disturbed it for a very long time. H1 is very easy to disturb. So if a galaxy wanders past, it'll start pulling on the H1 because it's just fluff and it's susceptible to that gravity. So you can disrupt the H1 very easily. The stars, not so much. The stars are quite tightly bound. They stick together. It's hard to disrupt stars, but it's easy to disrupt H1. So when galaxies interact, usually the first sign that you know they're interacting is shown in the H1. So that's what's shown here. This is another galaxy. This is NGC 895. In the center there, it's a spiral galaxy. Looks pretty normal. Nothing much is going on. If you look in the H1, it looks very different. So the red is H1. There's a hole in the middle. That's pretty common. It just means that basically it's all used up in the center. It's made all of its stars and there's no more H1 in the middle. So that's pretty common. But these two arms that are coming out in either direction, those are tidal arms, which means that a galaxy has wandered past at some point in the past and started pulling the H1 out of the galaxy. And from the stars, you would never know that. The stars look undisturbed, but the H1 does look disturbed. So you know something about the past of this galaxy that you wouldn't have known otherwise. And there's that little galaxy at the top there, which is also detected in H1. That's probably at least partly responsible for pulling this gas out. There's another one off the top right that is also a probable candidate for being the thing that went past and started disrupting the H1. So H1 can tell you about the past of a galaxy as well, what it's been through. So if we look back at our picture of the neutral hydrogen in the Milky Way, if you look down at the Magellanic Clouds, the H1 is also being pulled out of them, and it's because the Magellanic Clouds are interacting with the Milky Way, and the gravity from the Milky Way is pulling the H1 out, which is obvious in the H1. If you look in the optical, you wouldn't necessarily know that. So it tells you things you wouldn't have known otherwise. Okay, so finally, getting on to the stuff that I work on. So I work on galaxy evolution, which is how galaxies change and evolve with time. Controversial statement from some people because some people spend their whole lives working on this. I summarize it in one bullet point. Stars form from gas. It's ignoring a lot of details, but that is the truth. Stars form from gas. If you want to understand how stars form, which a lot of people in astronomy do, you also have to understand the reservoir material from which they're built, and that's the H1. And you have to be able to observe this as a function of time. So this is kind of a strange figure. It's probably the most intensive part of this whole talk. Along the bottom is redshift, or if you like, it's look back time, or if you like, it's also distance. 0 is now and here. Increasing numbers is further back and further away. On the y-axis, basically, if you go into the universe and you put a big cube of volume and you count up all the H1 in it, and that gives you a density. And then you put that cube at a further distance, count up all the H1, put it at a further distance, count up all the H1. That's how you build up the points on this figure. So there's a lot of points. A lot of people have had a go at it. It's a lot of scatter, I would say. Part of the problem is that these kinds of observations that I've been talking about, like actually looking at H1 in galaxies, that's the part of that figure that we can do that with. And there's 3 points, and they also don't agree. So in the past, people have spent all this effort of trying to observe H1. That's as far as they got, and their answers don't agree. At very high redshifts, so very high or large distances or a long time back in the universe, there's a different observation you can make. It's kind of similar but different. You do an observation and then you make an assumption and then you link that to something else and then you link that to something else. And you get all of these points and they're okay, but it's measuring something slightly different. And then in the middle, there's sort of not much. All of these points are assuming a lot of things. They start with one thing and then they assume something and then they assume something else and they assume something else. And that's reflected in the scatter, right? These points don't even agree. We have no idea what happens to the H1 at this point in the universe. And that's a shame because this point in the universe is actually action-packed. There's the most amount of star formation going on, the most amount of mergers in galaxies, there's accreting black holes, there's just a ton of stuff going on at exactly that time, and we have no idea what the H1 is doing. And the H1 is underneath all of it. So this is part of the reason for MeerKAT and also the SKA, is to observe the H1 at this point in time in the universe so we get a full understanding of how galaxies change and evolve. So MeerKAT is a beautiful telescope. It is owned by South Africa. They are generous enough to allow anyone to apply to use it. You don't have to be in South Africa or a South African. It's a very good telescope, so everyone wanted to use it. And it is often more efficient from the telescope's perspective to collect people into groups and say, you all have similar ideas, you all have similar goals, you are all asking the same question. Go form groups, collect together, and then submit one big project. That's what MeerKAT did, and they've got 9 big projects, these large survey programs they're called. MIGHTY is one of them. Everything needs an acronym. So MIGHTY is MeerKAT International Gigahertz Tiered Extragalactic Exploration. It's led by Matt Jarvis, who's in Oxford, and Russ Taylor, who's in Cape Town. It measures H1. It also does radio continuum, so the synchrotron radiation for the supernova remnants and stuff. It's not the deepest, so it's not going to do the most sensitive observations. There are other things that do more sensitive things. It's also not the biggest in terms of coverage in the sky. There are projects that look at bigger parts of the sky, but it's sort of a nice compromise in between. It's deep enough, it's wide enough, it covers 20 square degrees, which is good enough to properly sample the general universe. So this isn't looking at specific galaxies, it's just pointing at the sky and seeing what you get. Within these big teams, there's like 150 people or something in MITE. There's projects, working groups. I'm in charge of the H1 working group, which is coordinates all the H1 science. I chair that with Brad Frank, who's in Cape Town as well. So we're in charge of all of the H1 science that comes out of this large project. So we have some data. Data is released in phases, right? You don't get all of your data immediately. You do some observations, you release some data, you do some more observations, you release some data. So this is our phase 1 data. We pointed the telescope at the sky. You detect certain galaxies in H1. We detected about 300 of them so far, just a fraction of the observing. So this figure shows those 300 galaxies. Each dot is a galaxy. On the y-axis, you go and measure H1. You can convert that into a mass. So then you know the mass of gas that's in each galaxy. Along the bottom is, again, redshift or distance, look-back time. And then that black line is effectively the sensitivity of the observations. And this shape is very common. So it's not, there's no galaxies detected down here, and that's fine. It doesn't mean that there aren't any small galaxies at that distance. It means they're too faint to see. You can only see the faintest ones when they're closest. So this is these here. This is our sensitivity. For reference, this is the sensitivity of what I would consider to be the previous best project that observed H1. So anything, you can see anything above the line of your sensitivity. So we can see a factor of 10 deeper than the existing best survey. The existing best survey also cut out, it had a redshift limit. You couldn't see beyond that. So all of these galaxies on the left you couldn't see. It just didn't have access to them. We do. So our distance limit is much higher, goes off the end of this figure. And then just for reference, this covers 1 billion years in the universe. So these galaxies on the right-hand side we're seeing them as they were 1 billion years ago. So we've got little galaxies, we've got big galaxies, and we can look at this picture again. The big galaxy down the bottom, 10 to the 10 solar masses in H1, which is a pretty big galaxy, nothing special. And then that little one at the top is sort of a factor of 300 smaller, much, much smaller. So again, that's what the H1 looks like. You can either have a little blob or you can have a big disk. So there's also something else that's visible in this, is this. Galaxies aren't evenly and smoothly distributed in the universe. And we saw that from that movie of the simulation. Galaxies clump together, they cluster. And this is a galaxy group. So galaxies cluster together. This is a picture of a galaxy cluster. All of the sort of yellow galaxies, the galaxies that are all the same color, they belong to a cluster and they're gravitationally bound. So clusters are the biggest gravitationally bound structures in the universe. And there can be thousands of galaxies in a cluster. So we found a group, which is just a small cluster, a group of galaxies. So this is now data again, and it steps through velocity again. I've put little circles where the galaxies are because they're not so bright. There'll be little yellow blips. So if we step through, you can see in the circles little yellow blips popping up. And these are all of our galaxies in this group. And they're all detected in H1. So just for interest's sake, this is the kind of data that we got. I spent about a month and a half staring at data like this, going through, putting little circles. And you can only do that for a certain amount of time in a day before you start. So I did all this by hand. I would not recommend it, and I certainly won't do it again. So this is what that galaxy group looks like. In the center, there's an optical image that's just the sky, and then each of the little postage stamps around the edge are all of the galaxies in the group, and then the red line around them shows the extent of the H1. And there's some interesting stuff. There's the top left there's colliding galaxies. Those are galaxies that are about to merge. And there's tiny little galaxies. This is very small. There's very strange galaxies, quite irregular. Then there's these big sort of normal spirals that you would expect from H1 observations. So this was the first science paper that we had from our working group. It was led by Shilpa Ranchod, who was a master's student in Pretoria. She's moved on to a PhD in Germany now. So we discovered this group of galaxies. There's two weird things about this. One is that this is not a patch of sky no one's ever looked at. This is a very well studied patch of sky. Everyone with a telescope has looked at it. Nobody saw it. And people do look for groups, and nobody saw it. But it's super obvious in H1, right? You look at the cube, they pop up everywhere, you go, oh, there's a galaxy group, done. Nobody saw it. So that's strange. The other strange thing is that we thought H1 doesn't like being in groups. It doesn't like being in galaxies in groups because they interact with each other, and it pulls the H1 out and starts disrupting it. And so that's what we thought, that you couldn't have a group this size with every galaxy having H1, that you would thought that it would have been disrupted, or it would have been stripped out or used up, or so it didn't fit that we have this galaxy group where every galaxy is H1, and that was not in our experience. That's what we thought. So these new observations are maybe showing us things that we couldn't see before and we didn't know before. So now we have to change how we think about how galaxy groups work, how H1 works in galaxy groups, and how that all fits together. So that's effectively the end. I'll just summarize here. H1 is a little bit niche in terms of astronomy, especially in terms of physics. I think it's useful enough to be mainstream, and I think the SKA is going to make it mainstream. That's my goal. That's why I do these talks, to tell people how interesting H1 is. I hope I've convinced you that it does depend on which telescope you use to determine what you see. And H1, which is the stuff that stars are made from, and in fact the stuff that everything's made from, only emits at radio wavelengths. So that's a good motivation to build radio telescopes to see this fundamental material. H1 is quite useful. It tells you about dynamics. It tells you about how galaxies spin. It tells you about interactions, if the galaxies have been pulled apart. It shows you structures that maybe you didn't see before, like that galaxy group. MeerKAT is amazing. It is already making discoveries. This was just one of them. There's a number of discoveries it's made just because it's so sensitive. It's showing us things that we couldn't see before. The dishes in MeerKAT become part of the SKA. The SKA builds on the MeerKAT array. It builds it out. So MeerKAT will still exist. It'll just be like Super MeerKAT at some point. So you get more dishes, which means better sensitivity. You get longer baselines, which gives you better resolution. And if you have a better telescope, then you make new discoveries. And when you have new discoveries, this is a growth area. So this is why I think the SKA is such an exciting project to be involved in, because there's all this new parameter space that's just waiting to be discovered, and there's a lot of room for people to work in it. So that's why I work in it, and that's what I do. So I'll stop there.
We could probably have questions for about 10 minutes, so does anyone have any questions?
I was wondering, you know, when you were showing a galaxy that was being like pulled apart in the H1, why did you see that banding of like the H1 on a picture, or is it complicated?
No, it's a bad picture.
Oh, okay.
Yeah, it's the data is not fantastic because it was not really meant for this.
Okay.
So do you mean down the bottom
I
there?
see the kind of like
Yeah.
lines.
So that is, it's also kind of far out in the field of view. So the data, let me see how I can phrase this. So that's well spotted. It's a problem with the data. Oh, no, I won't. A lot of things emit in the radio, like mobile phones, cars, TV, radio. There's all of this ambient noise, basically, and it interferes with, it's called radio frequency interference. It interferes with the data. And that's part of it, and also other really bright things. You know, if you're looking at something bright, it sort of ruins the whole thing. There is something really bright in this image to the north, which sort of ruins it as well. So it's part of the data. It's not so much part of the galaxy, but it's well spotted. I mean, if you want to, yeah.
At the telescope in West Virginia, there's very strict restrictions on like mobile phones and televisions and stuff. So is that the same in South Africa, in the kind of MeerKAT area?
Yeah. So you also can't have spark plugs in a car. All of the cars are diesel because the spark creates RFI, it's radio frequency interference. So yeah, all of the people who lived near MeerKAT, and there's not many of them, they're not allowed mobile phones anymore. And like Wi-Fi, you can't have Wi-Fi at Green Bank. So things like that. And I mean, there's various problems with these things. There was a story about, there's a telescope in India, and they could see in their data that there was something. So they just drove around looking for what it was, and it turns out someone had an electric fence that was sparking that they were detecting, and it was, you know, however many kilometers away. You can't have microwave ovens on site, or you can't use them when people are doing those observations. So yeah, they're sensitive. Yeah. So go ahead.
Hi, I just have a question about the principles. You said like we can detect H1 because flipping the spin, and you also said that it takes some time. I don't know how long it takes, but does that mean if that doesn't happen, there's a large mass that's undetected?
Yeah, I would think so, yeah. So there's conversions to take that into account. So if you had one atom,
Yeah.
you have to wait 10 million years for it to flip. If you have 10 million atoms, you have to wait 1 year. On average, one of them will flip, sort of thing. If you have a gajillion atoms, they'll be flipping all the time. You know, one will be flipping all the time. And so you measure some flux, and then you know the probabilities with that transition. You do statistical mechanics, and you say, okay, well, if I see this many flipping their spin, that means there's this many in total. And that gives you the total mass.
Any other questions? If not, we'll call it a day. Thank you very much, Natasha. Donuts from Bizbar. I'll do this. Thank you so much. That was so good.
Oh, good.
I love that.
I felt so bad because I was so sleepy, but also I was like,
Stop. That's all done.